Let's move on to our next topic, that is Nernst equation, which is the most important topic of this chapter. So let us first discuss what is Nernst equation. Nernst equation, it determines the potential of the cell under non-standard conditions. It determines what? It determines the potential of cell. Okay. The concentration of species, it needs not always be unity. That is, it is equal to unity, but not always. Okay. For overall reaction, we can see an example here for Nernst equation. We have taken an equation here, or say we have taken a chemical reaction here, where M we are taking for a metal. Okay. And it is having N positive charge, or say this number of electrons it has, and it is present in aqueous solution, and it is getting what? Say M is copper 2 positive. Okay. What kind of reaction is this? Is this oxidation reaction or is this reduction reaction? So as you can see here, the copper, it is gaining 2 electrons and it is attaining stabilized, or say neutral state, okay, after the reaction. So this is an example of reduction reaction. So how we write this reaction or such type of reaction in a Nernst equation? Okay, that we need to know that Nernst equation we represented as E, that is for electropotential, and what is happening to that electropotential. Here in the given reaction, Mn positive, it is getting what? Reduced. Okay, it is gaining electrons. Okay, formula for writing the Nernst equation is for any concentration that is equals to the standard electrode potential okay minus RT by NF. This R is what? This is gas constant. Okay, value of gas constant is what? 8.314 joule, Kelvin inverse and mole inverse. Okay, T is for temperature. It is generally equals to 298 Kelvin. Okay, many a times it is given in the question. F is for Faraday's constant, and value of Faraday's constant is 94687 Coulomb, mole inverse. These are all mentioned here. Okay. So here an example is given for Nernst equation. See, this is a general equation. Okay. And for this, how we represent Nernst equation? By using this formula. Or we can take another example. Let us take another example here. For for the same reaction that we have done in the previous electrochemical cell for copper and zinc. How we write the next equation for that? Copper to positive. What was happening in that reaction? Copper to positive, it was getting reduced. Okay. And zinc, it was getting oxidized. Right. So write a Nernst equation for this reaction. Let's try to write Nernst equation for this reaction. So first we are going to write for the copper. Using this equation, okay, or you can use this where Q is what? It is the reaction constant. Okay, you can use any of it. So for electrode potential, that is E cell we are using copper 2 positive to copper. Okay, that will be E naught, the same equation or same cell, copper 2 positive to copper. Okay, what is next? Minus RT by NF natural log. This ln is what? It is natural log. Okay, 1 by copper 2 positive. Right. Similarly, we can write for this reaction is taking place at what side? At cathode or anode? At cathode. Okay. So let's write the anode side reaction. At anode, what reaction is taking place? This. Can we write Nernst equation for this? Using this? Yes. Zn will be Zn2 positive. Okay. That is equals to standard electrode potential for Zn to Zn2 positive. Okay. Minus RT and F natural log 1 by Zn. Zn2 positive. Okay. So now we have written Nernst equation for this cell representation. Now we have to solve these two equations. Okay, how we are going to solve this equation? By using this formula. Let me change color here. So you are going to use E cell is equals to, you are going to subtract these two equations that we have written. First is this cathode minus anode, oxidation minus reduction, right? This is how we were calculating Zn, Zn2 positive. Alright, so we are going to subtract these two equations. Okay, so you can see these things, the RT, this RT by NF and natural log and RT NF by natural log, these are common here. Okay, so we can take this as common and they are actually very easy to solve. Okay, we can take them common and by solving them, by putting in this formula, what we will get? We're gonna get the standard electrode potential. Okay. The E cell, it would be equal to E cell naught minus RT and F. Okay. Multiply Zn2 positive and copper 2 positive by solving these two reactions using this formula. Okay. So you can try this on your own. All right. So here equilibrium constant for Nernst equation we used is Kc, which is very important. Okay. As you know that how we represent a chemical reaction in Daniell cell, this is, the concentration, it keeps on decreasing for copper 2 positive ion, while for Z2 positive, it keeps on increasing. Okay. But after some time, When an equilibrium is maintained, the concentrations for both the ions they become equal. Okay, concentration for both the ions they become equal, and we can read this on voltmeter when the reading on voltmeter becomes zero. What that means that the concentration or the reaction taking place between these two have achieved an equilibrium. Okay, so for that E cell becomes zero. Okay, and that means that the Zn2 positive and copper, the whole reaction, it has attained equilibrium, and that is why a constant developed there, which is known as Kc, or say Nernst equation constant. So where we use Nernst equation constant when the oxidation and reduction reaction in electrochemical cell they attain same or say equal concentrations. All right. So this was for Kc. Obviously there is a setup for constant between the electrochemical cell when the salt bridge was doing what? It was maintaining the balance of charge, okay, and maintaining neutrality in the chemical reaction taking place in the salt bridge, okay. And when an equilibrium state attained, then while solving the reduction or say redox reaction or say redox couple using Nernst equation, the equilibrium attained or equilibrium constant attained from the Nernst equation, it is represented by Kc. Okay.